So we come to our last talk of the day from Professor Alan Fitzsimmons of Queen's University Belfast, who is an all-round good egg in the cometary world. He's a very well-known professional comet astronomer, but he's also very supportive of us amateurs and work with amateurs. I think he's the only speaker today who's actually got a comet named after him. But, and it's a big but, he does not have a Blue Peter badge. So Alan's going to talk to us today about exocomets. Thanks, Alan.
Thank you, Nick. So I'd like to start by thanking the BAA Comet section to invite me to speak here this afternoon, because it's a bit of a, well, not quite a homecoming for me, but 39 years ago, as a young undergraduate university student, my summer job was working up the hill there, swinging around the 28-inch refractor in the Onion Dome and impressing hordes of Japanese tourists for, I don't know, Victorian technology. And so it's very nice to be back. Now, the subject of my presentation this afternoon are exocomets, comets around other stars. Why should we bother? I mean, you've already heard from Jonathan, we actually have about 60 new comets discovered around our sun every year now. We have perhaps a billion comets waiting to be discovered. I mean, why bother with comets around other stars? Well, first of all, again, I'm preaching to the converted. This is the BAA comet section. Every new comet is a good comet, right? But also, it comes back to why scientifically are we interested in comets? Our solar system comets tell us something about the formation and evolution of our solar system, apart from being glorious to view in the night sky. By finding and studying comets around other stars, then perhaps we can get better clues as to the general process of the formation and evolution of planetary systems throughout our galaxy. So this is what we're going to look at first in terms of general subjects in this presentation. How do we know exocomets exist in the first place? We're going to look at how we observe and know there are large populations of exocomets and other stars. We've got to look at the seemingly impossible idea of detecting individual comets going around other stars, and then we'll end with a brief look at what might be happening over the next few years. So, first of all, how do we know exocomets exist? Well, one of the reasons we're giving this talk is that, to be honest, I haven't really done much on exocomets in my career, but just before, you remember those halcyon days before COVID? Just before those times, I ended up working on these things. The first interstellar objects discovered in our solar system, both of which showed clear signs of a cometary nature. We had the first interstellar object discovered passing through our solar system from interstellar space, Oumuamua. Please ask Nick afterwards to pronounce that, it's so funny. They got it, well done, Nick, thank you. And then the second one, just a year later, interstellar objects are like buses, right? You wait decades for one, then two come along at once. 2I Borisov. Now, fair enough, Oumuamua in our telescopic images did not look like a normal comet, rather looked like an inert comet, also an asteroid, but subsequently analysis of the astrometry, the positions of Oumuamua, detected by both ground-based telescopes and from Hubble Space Telescope, showed it was undergoing what we call non-gravitational acceleration, which is most readily explained by gas that we could not see coming out. And given that in images like this, we're not sensitive to gas, just dust, this tells us perhaps this was a comet or a fragment of a comet, which for some reason that we still don't understand was emitting gas, but no dust particles. Whereas Borisov, well, look, boom, comet. You kind of recognize that one, everyone. And indeed, although it was very peculiar in terms of composition compared to most other comets we see in our solar system, this is clearly an icy object visiting us from another star. And so the question then is that, well, how many of these things are out there? Well, to answer that, we really want to go back and look at the lives of comets. Where do they form? How do they live? How do they evolve? And indeed, what we now understand, or we think we understand, certainly at the time of Oumuamua and Borisov, is that we have comets forming in the disks of material around stars when they're born, just at the same time as planets, because of the large gravitational perturbations, and basically it's a mess when solar systems form. Large numbers of those initially icy cometary bodies are ejected out into interstellar space to form interstellar objects. But some of them will survive in that protoplanetary disk, and you'll find them in various places. In the solar system, we find the main belt comets in the asteroid belt. We find the comets in the Kuiper belt, which are the progenitors of our Jupiter family comets. And we find, of course, the comets in the Oort cloud, which give us these long-period comets and Halley-type comets that John was mentioning earlier. And then we can split these up into further. We can say, well, from the Oort cloud, we get the Manx comets, the long-period comets, the Halley-type comets. The Kuiper belt gives us Centaurs and JFCs, and sometimes they may, as we've just heard, with things like Faithful, may be extinct comets, so maybe in that case we'll call them Damocloids, after Damocles, the first object known. But eventually they're all going to die. They're going to be basically hit the sun or hit a planet, or they're going to disintegrate in order to be ejected back out into stellar space. Comets live very interesting lives. If you're going to find them around orbiting another star, probably the first kind of place you'd look would be the analogous to our Kuiper belt. Now, this is a lovely graphic that was drawn up by NASA in support of the New Horizons mission, which, of course, back in 2015 gave us our first close-up images of Pluto, and a few years later, our first close-up images of a trans-Neptunian object or a Kuiper belt object. And we basically now know that beyond the planet Neptune, we have a large belt of cometary bodies that out there are inert. They're far too far from the sun for the surface ices or the subsurface ices to sublimate and release gas and dust. They sit there, if you like, in deep freeze until perturbations, generally by Neptune, will end up perturbing them or tweaking their orbit such that they start moving in towards the inner solar system, where millennia later we see them eventually as Jupiter family comets. Now, this scale here, remember that Neptune is 30 astronomical units from the sun, 30 times the distance from the sun that the Earth is. And so the Kuiper belt, as we know it, stretches from just outside Neptune's orbit at about 39 AU, out to about 44, 48 astronomical units, although we do have objects that are on much more distant orbits out there as well. Now, if we look at nearby stars, we generally cannot see the inner region, or we cannot resolve the inner region still at the moment, where we'd find Jupiter family comets. But we can actually try to see this region here. And we do actually see that region. We see these Kuiper belts all over the place. These are images taken by the ALMA observatory. This is a sub-millimeter radio observatory run by the European Southern Observatory, the National Association for Observational Astronomy in the US, and also by Japan, based in the Atacama Desert down in Chile, and it's basically the most sensitive instrument we have for observing the universe at very short radio wavelengths. It's a millimeter or sub-millimeter wavelength. Normal radio telescopes operate on scales of centimeters, so that you could actually easily fit a wavelength of light between your thumb and your first finger. Millimeter waves are about a millimeter long. And in these images, we can see these beautiful disks of material around these stars. Now, what you're seeing are not large objects. when you observe at a particular wavelength of light, most of the time you're most sensitive to objects about that size of wavelength. So as these images are taken of material at millimeter wavelengths, what you're looking at are accumulations of basically dust around about a millimeter in size. And this immediately tells you that something is going on in these stellar systems. Let me explain. Let's explain by going to this beautiful image that I still think is fantastic, almost 10 years ago, after it was first taken by ALMA, of the millimeter-sized dust grains around the star HL Tor. Now let's just look at this for a minute. We've got all this dust in these various rings. We've got gaps in the rings where there may be planets forming, sweeping out the gap, those kind of trenches in the dust. In terms of scale, going from here to here is 60 astronomical units. The whole of our solar system out to Neptune would fit in here. So this is a big planetary system that we're observing in the first stages of formation. And yet, if things were constant, we wouldn't see it. If we look at how that dust moves as it orbits the star, it undergoes something called the Poynting-Robertson effect. Now, this is an effect due to, funnily enough, it's similar to the aberration of starlight. It's an effect of special relativity. But as that dust moves and orbits the star, effectively it feels almost like a headwind because it absorbs the radiation from the star and it heats up. But then when that radiation comes out, it comes out in a slightly different direction. And so the Poynting-Robertson effect for dust grains about 1,000th of a millimeter or 1 micron in diameter up to millimeters in diameter feel this kind of headwind, and they'll slowly spiral in to the star. So dust grains that are larger than about 1,000th of a millimeter or micron or larger will slowly spiral into the star. And we're familiar with that here on Earth because that's what forms the zodiacal light. When we see the zodiacal light in the evening sky or the morning sky, those are dust grains from comets in our solar system that haven't made it into the media streams or remained in the media streams that John has just told us about, but are just simply slowly spiraling into the sun until they're vaporized. Well, so the bigger dust grains should be falling into the star. The smaller dust grains don't hang around either, because dust grains less than about a micron across feel the effects of radiation pressure, the same thing that blows out dust from a comet coma to form the dust tail. And so the small dust grains should be being ejected from the system, whereas the larger dust grains should be spiraling into the system. This can't exist in a steady state. It can't just sit there. And what these two physical effects tell us is that, well, maybe we're just observing the wrong wavelength. Let's have a look at another star, very famous star with a disk around it, Fomalhaut, at different wavelengths of light. Remember, each wavelength of light is sensitive to a different size of dust grain. Here we have this annulus of dust imaged by the Hubble Space Telescope, observing the optical wavelengths. So here we're dealing with truly microscopic dust grains. Here we see images from the James Webb Space Telescope released recently. And here we're looking at dust grains at about maybe 10 or 100 times larger. Then we could go to larger wavelengths, longer wavelengths, see larger dust grains. We can use the Herschel Space Telescope to get even larger dust grains, and finally to ALMA, where we've got those millimeter dust grains again. We see dust grains of all sizes in this disk. Where are they coming from? They're coming from collisions. So we don't see these individual objects in these disks, but what we're seeing is something that can't exist unless there's a continuous supply of new material caused by collisions between objects in those locations. And what are these locations? Well, remember, we're talking about objects that are tens or hundreds of astronomical units away from their parent star. These will be icy planetesimals, what you and I, in this meeting, would call a prototype comet nucleus. So the existence of these debris disks tell us that what we're looking at is the debris from collisions of these cometary bodies surrounding these stars. So we know that these stellar systems have belts of exocomets around them, just as our solar system does in the Kuiper belt. Hold on, you might say. Hold on. Right, we see dust, but we know comets have got lots of ice in them. So surely, when you have a collision, then we should also see this ice released, maybe in the form of gas. Well, you do. Again, ALMA can detect not only the large dust particles in these disks, but it can also then, the receivers can be tuned to look at particular wavelengths where we might expect to see emission from gas. And that's what we see. So here we can see a debris disk. Actually, I do apologize, I haven't put the star on. Sorry, I do apologize. But here we can see a debris disk. And again, look at the scale, that's 100 astronomical units. So this is quite a large disk compared to our own Kuiper belt in the solar system. But here we can see the emission from carbon monoxide. In fact, not just normal carbon monoxide, but carbon monoxide with the isotope 13C in it. And we can compare that to the emission when we tune to a different frequency where we don't see the gas, we just see the dust. We can compare that to the dust distribution, and one can see large similarity. Not only with that, because here we're detecting the emission due to gas, ALMA's, remember, a radio telescope, it can measure very accurately what the wavelength is of the gas that it sees. So you convert that into a Doppler shift, you can figure out how that disk is rotating. So if we measure the wavelength of the carbon monoxide at each position on this, we can see that this side of the disk is blue shifted, it's moving towards us, and that side of the disk is red shifted, that material is moving away from us as it orbits the star. So here we see some beautiful evidence that what we're seeing is a belt of icy planetesimals, if you like, exocomets, being ground down through collisions. And that's a lovely example. Let's look at another example, a star we'll come on to in a minute, Beta Pictoris, the second brightest star in that constellation, which has a very prominent disk of dust that's pretty much edge on to us as we view it from Earth. And here we can see, actually what we can see here marked in this position is the position of the star and a giant planet that we know it orbits that star, Beta Pictoris b. This is it in dust. Here's the gas distribution. The dust is, it's a bit clumpy, but not as clumpy as the gas, the carbon monoxide, being released in these collisions. And in fact, there's a couple of ways you can interpret these pictures. You either assume that this clump is on the far side of the star, in which case there are things rotating around like this, and what you're just seeing is well, they interpret it as possibly a clump caught in a resonance between planets that may exist in that disk. Or you can interpret it another way, in which case there's been a collision, not between cometary planetesimals or planetesimals the size of comet nuclei, but a couple the size of Mars. And if you've got that, then this is the picture. And to be honest, it is difficult to know which of these is true. But here we can see then the evidence of disks of cometary planetesimals around other stars. Now, of course, the solar system has two reservoirs of comets. Yay, twice as many for us to look at. We've got the Kuiper Belt, giving us the Jupiter family comets, and we've got the Oort cloud, much further out, 10,000 astronomical units and more, most of the comets there, which give us our long period comets. Now, out there, temperatures are really low. You're probably talking just a few degrees above absolute zero. And one might expect that because even though you may have 10 to the 11, 10 to the 12 or more comets in an Oort cloud, that would be incredibly impossible to detect around another star. But we do have very sensitive instruments now that could go to very long wavelengths and try to detect that thermal emission. In fact, there's been a recent study just a few years ago using data from the Planck mission. Now, the Planck mission was sent up to keep all the cosmologists happy, not the planetary scientists, okay? It's to detect the fluctuations in the microwave background with 300,000 years after the Big Bang. But it's incredibly sensitive. And so about 5 years ago, yes, Baxter et al. Said, okay, let's look at the brightest stars within about 80 parsecs of our sun. And let's see if we can see any increase in emission above what we might expect at very long wavelengths, emission that might imply there's some very cold material orbiting that star at tens of thousands, 20,000, 30,000 astronomical units out from that star. Now, most stars, they found, yeah, there's probably nothing there. But there were a handful where, yeah, there could be some excess emission, very small amount of excess emission at a few 10,000ths of an AU from that star. This is probably the best it's going to get, and it's not clear what we'll be able to do in the future, but there's some tantalizing evidence here that maybe some of the nearby stars have not only Kuiper belts around them of exocomets, but even Oort clouds around them. But that's going to require some extra work in the future. Let's go back to Beta Pictoris, because it is probably the most heavily studied young planetary system in the sky. And it's because of this image in 1984 that was taken by Smith and Terrell, by putting a chronograph in their telescope, looking at nearby stars and realizing, oh wow, we can see this. Now, that was state of the art in 1984. I'll just point out that I think it was less than 10 years ago, this has now been imaged by amateur astronomers. Now, of course, you're going to have to go down to Australia to see it yourselves, but it's worth the trip if you can try it. Now, but of course, that was state of the art in 1984. We now have instruments like the Hubble Space Telescope and the James Webb Space Telescope, of course, with their chronographs on board. And these are images taken over 15 years by the Hubble Space Telescope, showing you, again, the structure in this edge-on disk of material, including these lumpy bits, this structure in the disk, which is difficult to disentangle because it is edge-on. But again, remember the scale here. That bar is 100 astronomical units. So all of our inner planetary system fits in the bit that's been blocked out. Saying that, astronomers are getting pretty good at blocking out that star, right? So here's images from the Very Large Telescope and the SPEAR instrument that was built specifically to look for planets and material near nearby stars. And oh, sorry, it stopped. I thought the movie would continue playing. But in this image, Beta Pictoris has been blocked out, and this is the gas giant planet Beta Pictoris b, which when you saw the animation, let's see if I can get it going again. If I click it, yay, there we go. You can see between 2014 and 2016, moving around the star. Amazingly, since then, another giant planet has been found in the system, even closer to the star, actually within Jupiter's orbit if it was in the solar system. And so we have at least a two giant planet system orbiting or around Beta Pictoris C. But these are giant planets. Again, let me go back to something I said at the start of this talk. It'd be crazy to try to see comets. We can hardly detect, or just about detect, giant planets. And these planets, by the way, are significantly more massive than Jupiter, about 8 or 9 times the mass of the planet Jupiter. And yet, you can. Because I'm now going to turn to, where's Robin? Something that Robin probably can't quite try to get at the moment, but I wouldn't put it past him. High resolution spectroscopy, or as a friend of mine always called it, wiggly line science. So wiggly line science basically says, we've had the talk from Robin, which basically says that you can take a spectrograph and split the light coming from an object, in this case Beta Pictoris, into amount of light versus wavelength. Now this is a very high resolution spectrum taken with something called the Hart's instrument on the 3.6 meter down at Lucia at the European Southern Observatory. And I've just plotted a bit of a spectrum just around what we call the calcium H and K lines, which you see very prominently if you take a spectrum of the sun or anything else. And in fact, in Beta Pic, you get the one calcium line, and here's another calcium line. This one looks wider because there's also hydrogen superimposed on it. So let's stick with this one. And let's zoom in to this spectral line here. So very high resolution. And what we see is the absorption line due to the ionized calcium, calcium-2 in the star, plus a narrow bit here, and that is the ionized calcium in the disk of the circumstellar disk between us and the star. So we're seeing the gas in the disk. Now that's fine. We know the disk is there. We saw it with those wonderful images. But now let's take a look even closer, just at the base of this line, and take not just one spectrum, but let's take one spectrum one night, and take one spectrum another night, and take one spectrum another night, and I'll color code them in the colors I like because it's my talk. And what you can see is that it's never quite the same. So here's the base of that absorption line at very high resolution. We're splitting up this light now really finely in wavelengths. And we can see that, well, here's the base of the absorption from the gas in the star. Here's the absorption from the gas in the disk. But then every time we take a spectrum, it kind of looks different because here's this purple spectrum. Here's one. Oh, look, there's an extra bit of absorption there. And it goes back up again. Here's orange, and well, we don't have that purple absorption that was blue shifted the day before, but now we've got this kind of red shifted absorption. And now we've got this red, and the red, oh, look at this. Actually, I forgot to mention this. What's going on here? There's an extra bit there. I don't know what's going on. Slightly blue shifted. And then what have I got in green? I've got green, oh, there's another bit here. So anyway, what's going on? Every night we take a spectrum of the star, we see something different. And in fact, if we take spectra over the night, if we just stay looking at the star and take spectrum after spectrum after spectrum, we see this material slowly changing, moving either towards us or away from us. Well, amazingly, it's because every time we see a dip like that, each one of those is caused by an individual exocomet orbiting that star. What's happening is it's going between us and Beta Pictoris as it orbits the star. It's releasing calcium atoms, which is then being ionized, so we can see this absorption line, and we actually see them moving across the face of the star. We don't have a picture, but we can detect them spectroscopically. And amazing thing about Beta Pictoris is that you see these every night. I mean, seriously, it's hard to find out what the spectrum of Beta Pictoris should be without a comet passing in front of it. because that's a very, very rare event. In fact, there was a paper published by Kiefer in 2014 where they analysed, I think it was 6,000 individual absorption profiles from 6,000 individual exocomets passing in front of that star as they orbited the star. And what they found was that, well, there are all kinds of shape sizes, but you can split them into two. So for example, if you look at how fast they're moving relative to us, are they moving towards us, are they moving away from us? They found they could split it into two groups. There's a group which are basically really hardly moving at all towards us or away from us, so they appear very central in that spectrum. And then there's a more broad group that kind of can range over a wide range of velocities, going from minus 100 kilometers per second, 100 kilometers per second moving towards us, to 150 kilometers per second moving away from us. And they also found that things like that correlated with how wide they are. And when they put them together on a plot like this, because once you start doing the orbital analysis, you can actually work out some idea about what the orbits of these comets are. And here again, they use the same color coding, blue for these what we call rather deep absorptions that are very relatively slow moving towards us or away from us, and the red faster moving comets. And you can see that if we look at, when you try to figure out which orbit they're in, what the longitude is of periastron, i.e. the closest point of the comet to the star, the fast moving objects, they go around quite a wide range of velocities, whereas all the slow moving objects, they all seem to be coming in the one point. And we actually believe that this is because these comets here are trapped in a resonance with one of those giant planets. It's probably the 4-to-1 resonance with Beta Pictoris b. The other thing is that when you've got a solution like this, when you try to calculate, we use these velocities and their appearances and how the velocity changes, you try to calculate the orbit, what you get out is the perihelion distance. You don't know the eccentricity, but you do know how close, or you can estimate how close that comet is coming to the star. So let's have a look. On the right, we have the Sun. And just point out that here's the Sun, we're at 1 AU, and if we're lucky, long period comets and short period comets come into about 1 astronomical unit from the Sun. Those two families of comets at Beta Pic getting much closer. The faster moving comets go within 0.08 AU of the Sun, of Beta Pic, I should say. That's how close they get to that star. And the slower moving comets are still coming in close, but it's about 0.15 astronomical units. Now, why is this important? Well, the closer you come into a star, the hotter you get. And we can also take into account that Beta Pictoris is an A2 main sequence star. So it's hotter than our Sun. It's over 8,000 degrees surface temperature, and it's larger than our Sun. It's about 1.8 solar radii. So you can work out, if you've got comets coming into these distances, what's the temperature going to be like? Well, again, if we look at the Sun, of course, at 1 AU from the Sun, comets are going to get to a temperature of about 300 Kelvin or so on the surface, and that allows you to sublimate all the water you want and all the other ices. But for the comets in Beta Pic, the more distant comets are reaching a temperature of 1800 Kelvin. Oh, by the way, sorry, this is Kelvin. I should have put it in centigrade. Subtract 273. 1500 degrees centigrade, 2200 degrees centigrade. At that temperature, rock melts. And that's why we see the calcium, because it's not just ices that are melting in these objects. It's everything. Everything is sublimating. It's just a furnace on the surfaces of these exocomets when we see them pass in Beta Pic. In fact, one can ask, that would be the same whether or not it's a comet or an asteroid. let me just put it this way. I'm in the BAA comet section presentation. These are things that are sublimating whatever. They're comets. Okay. Now, that's Beta Pic. Beta Pic is not alone. Since these objects were first really observed about 30 years ago, that we've identified about 30 other systems where you see these variable signatures in the absorption lines of the stars caused by something rapidly moving in and out from night to night in front of the star. Either we can see them in the ultraviolet with things like the Hubble Space Telescope, or we can just stick with calcium lines in the optical, or even sodium lines, where we also can see these exocomets. So we've got about 30 other Beta Pic-like systems where we can see individual comets, and that's amazing because we can detect the gas coming from comets orbiting these other stars. But as you know, there's two bits to a comet. There's the gas and or the ice, and there's the dust. Is it possible we could detect the dust? Well, this was first calculated, again, over 20 years ago by Le Cavalier des Étangs, where the idea is that you've got a star, and oh, do you like my graphic, by the way? And you've got a comet moving across it. What would you see if you're sitting with a telescope just measuring the brightness of that star from Earth several parsecs away? What's going to happen is that when the coma of the comet moves across the star, you're going to get it starts moving across the face of the star, you're going to get a very sudden drop in the apparent brightness of the star. Then the coma moves away, but you've still got the tail behind it. So the shape of the light curve would be, much more gradual. The star would return to its normal brightness much more gradually. So if you think of this as an inverted shark's fin. So that's the kind of signature you might want to look for, except this is a good theoretical calculation. You can see what's happening here. The star is here, the comet moves around, here's the coma, here's the dust particles streaming out and forming the tail of the comet. This is what's giving you the shape, but look at this. The change in brightness is less than 1/1000th. So you need an accuracy of 1/1000th of a magnitude to even try to go for this. And back in 1999, there was no way you could do this. But hurrah for exoplanets. I never thought I'd say that out loud. The thing about exoplanets is that we know that many can now be discovered through occultations, where the planet moves across the star. But to actually detect Jupiter-sized planets, you need an accuracy of 1/100th of a magnitude. To detect something the size of the Earth, you need an accuracy of 1,000th of a magnitude. And there's been possibly too many exoplanet satellite missions launched in recent years to try to achieve this accuracy. And indeed, just 5 years ago, the first set of exocomet transits across the face of the star was found in data from NASA's Kepler mission. Around a number plate of a star. It's a F2 main sequence star, so slightly warmer, slightly larger than the Sun, but not very much. It's 10th magnitude, which meant that for Kepler, that's pretty bright, and it could do really, really, really high precision photometry. And in an analysis of the Kepler data, Rappaport et al. 5 years ago found 3 clear signatures as predicted of what you'd see if when a dusty exocomet with its coma and its tail moves across the front of the star. They also found 3 fainter ones, but there's clearly something there. So we can now detect individual comets around random stars. They actually, in the whole trawl of the Kepler database, they found 2 stars where they saw these signatures. This one where they found 6 signatures, and another star where they only found 1, so they're a little bit circumspect about that. But if you're going to see them around these stars, there's clearly one place you want to look, which is Beta Pictoris, where we know there are thousands of exocomets. Now, Kepler didn't look at Beta Pictoris, but TESS did. And Beta Pictoris is a bit of a problem when you do photometry of it, very accurate photometry. It's what's called a delta Scuti star. It basically oscillates in brightness rapidly. And so what you first need to do is to measure the magnitude of the star. And again, this is units of thousandths of a magnitude. And then you fit that. And in fact, this sequence of photometry has been fitted with 52 individual frequencies of vibration of the star. When you do that, you get a pretty good residual. So this is now just the random noise after fitting that signal. And then you can start looking for, oh look, Beta Pictoris also has transits of dusty exocomets and their tails. And in fact, in this paper by our old friend Le Cavier des Étangs, if they're in the audience, I apologize for my pronunciation, I failed O-level French, just published last year, they found 30 individual exocomets transiting the star. In fact, because there's 30 of them, if you assume that the amount of obscuration is proportional to the amount of material emitted by the nucleus of the comet, which then is proportional to the size of the comet, you can measure a size distribution of those comets now, those comet nuclei going around the Beta Pictoris, and compare it with the dashed lines with various efforts to measure the size distribution of comet nuclei in our solar system. And apart from one estimate here, it's pretty similar. It looks like comets orbiting Beta Pictoris have the same distribution of sizes of nuclei as we have in our solar system, which to me is pretty impressive. I do think this is lovely. So we now see that we've got families of comets around other stars, other main sequence stars with their own planetary systems. We're not done yet because we're all going to die. Or rather, the sun is, and probably us before it, modern medicine notwithstanding, we know that the sun is going to start off as, well, it's starting right now as the main sequence. It's going to eventually, in about 5 billion years or so, evolve off the main sequence to become a subgiant, then a red giant, then it says here, according to the BBC Science Focus, a new red giant. Okay, folks, this is an asymptotic giant branch star where the sun will go. Finally, at the end of the asymptotic giant branch, it will eject a planetary nebula. Half the mass goes out into interstellar space. You're left with a white dwarf. And white dwarfs are cool. Well, actually, no, they're very hot when they form. They cool down eventually. Here's our, I think, everybody's favourite picture of a white dwarf. Here's Sirius and Sirius B from the Hubble Space Telescope. One of our closest, and in fact, of course, the first white dwarf ever discovered and measured. Now, white dwarfs are effectively it's supposed to be very simple things. They're the cause of dead stars. They should have hydrogen in them. They should have helium in them. Some of them might have a bit of carbon. That's it. You'll get nothing else that you can see. Why? Because the gravity on the surface of a white dwarf, remember you're talking about something perhaps 0.6 or more times the mass of the sun, that's the size of the Earth. The force of gravity at the surface is so large that any heavy elements, boom, disappear into the center. The surface of a white dwarf should be very, very simple. And yet, some white dwarfs, when you take a spectrum of them, sorry, more wiggly line science, here's brightness against wavelength, and these are just offset by each other. You see lots and lots of absorption lines. Oh, yes, calcium, our old friend calcium again, good stuff. and lots of other stuff. There's magnesium and so on. What's going on? When I was at university, when I was kind of not enjoying myself up on the hill in my summer holidays, I was learning about white dwarfs and learning back in the 1980s that there are these things that they didn't understand. Where did these heavy elements come from? This is really strange. Well, they're called polluted white dwarfs. And indeed, the interesting thing about white dwarfs is that because we don't really understand how they form very well, you can actually figure out from their temperature, which you can measure from the spectrum, you can measure how old they are. Because once they form, there's no other energy, they're just cooling down. You can calculate the rate of cooling very, very accurately. And so if you've got a temperature of 25,000 for the surface temperature of a white dwarf, it's about 20 million years old. It's about 20 million years since it created its planetary nebula and just started sitting there. If you've got 10,000, a temperature of 10,000 Kelvin, you're about 1 billion years old. And if we look at any of these white dwarfs which are polluted, that's a nice word, isn't it? Polluted by these heavy elements, there's no real distribution with age. You can find polluted white dwarfs, the atmospheres of white dwarfs polluted by these heavy elements at all ages. Where are they coming from? Well, they're coming from planetary material falling onto the white dwarf. The planetary systems around these white dwarfs survive the red giant stage, the asymptotic giant branch stage, the ejection of the planetary nebula into space. And as that planetary system evolves, our current understanding is that because of the perturbations between that planetary system, as it rearranges itself, it comes up to a new configuration, that ends up throwing some of the original comets and asteroids inwards towards the central star, and some of them will eventually hit the white dwarf. Now, they don't get there, they don't fall straight on. There'll be perturbations will gradually move them closer and closer to the white dwarf until the white dwarf comes within what's called the Roche limit, the tidal force limit of the white dwarf. And then it's just literally ripped apart. And so what we see is signs not really of exocomets and exoasteroids hitting the white dwarf, but it's the disrupted remains of the material falling onto the white dwarf. And what we see when we actually measure the compositions of these pollutants, what astronomers find is that the majority of them actually look like asteroids. To be honest, you might expect that in our own solar system, right? Because the asteroid belt's closer than the Kuiper belt, so you expect more material perhaps from the asteroid belt to fall on to the white dwarf. And indeed, that's what we find. But in at least 3 now, when you look at the spectrum of the white dwarf, again at high resolution, and you perform theoretical modeling to model the absorption lines due to the contaminants. Here we've got silicon, here we've got oxygen, there's the calcium, again, there's the magnesium. When you do that modeling, you get back the elements, the elemental composition of what fell onto it. What you end up with is a water-rich body, which for you and me is a comet nucleus. And in fact, a beautiful piece of work, again, just 6 years ago now by Zhu et al. They looked at this particular white dwarf, 1425, and they looked at the elemental ratios of carbon, nitrogen, oxygen, sulfur, magnesium, nickel, and calcium, and matched them with the derived composition of Halley's Comet. And it's a match. So we now have evidence that comets are so good they can even survive the death of their parent star. Who wouldn't fall in love with these objects? So looking at the history of stars, or even the history of the solar system according to comets, we see exocomets at all stages. We know they form in star clusters, and in terms of planet formation, we see them from the disks of material around stars. We see them once those planetary systems are formed through Beta-Pic-like stars, and we see them after the stars have undergone red giant and asymptotic giant branch evolution in terms of their disrupted remains falling onto the surfaces of white dwarfs. And let's stick with this picture, because one of the most fun papers I've read recently was last year, where the investigators, Lee et al., said, okay, let's take our solar system and let's evolve the sun. Where do things end up, and what falls on eventually onto the solar white dwarf in 5 billion years plus? And it's interesting. What they found was that, well, as you might expect, when they looked at the main belt asteroids going from perhaps 1 million years after the sun becomes a white dwarf up to 1 billion years after it becomes a white dwarf, you've got a continuous rain of boring asteroids. Sorry, I shouldn't say that, but you know, a continuous rain of asteroids falling onto the white dwarf. The interesting thing is that the expansion of the solar system after the asymptotic giant branch stage will set up different resonances in the solar system, particularly things called secular gravitational resonances, and so we'll also get a bunch of Jupiter-Trojan asteroids falling inwards, falling on to the white dwarf. And then eventually, as we go up past 100 million years after the sun becomes a white dwarf, we'll start having the trans-Neptunian objects falling on, evolving, falling onto the white dwarf. So alien astronomers, or perhaps even us, in 5 billion years, will be able to go up, if we're, or anybody in an extrasolar planetary system, will be able to look back at that, oh look, there are comets around that thing that used to be the sun, which is, I think, very nice. So I'm going to finish now, just briefly. I'm just going to point out that this is where we are at the moment. What's coming up? Oh, there's going to be lots coming up in exoplanets. Oh, sorry, exoplanets? Oh, exocomets, apologies. First of all, 2 years' time, Rubin Observatory. And I like this shot because this was taken last month. So the Rubin Observatory is now there, at least the building is in Chile. The telescope's still being assembled and the camera's been assembled. But it's now planned to see first light in 2 years' time. 2025. Now, Rubin's going to be fantastic. It's going to find lots of normal comets for us anyway. It's going to find lots of asteroids, of course. It's going to find we've got about, I think, 4,000 or no, maybe 3,000, 5,000, something like that, trans-Neptunian objects. It'll find another 40, 50,000. It's going to be a powerhouse of discovery, along with other boring things like black holes colliding and stuff. But the important thing is that the Rubin Observatory should, with best estimates, find about 1 new interstellar object traveling through the solar system each year. So we'll be able to directly observe these exocomets that are visiting us. The year after, Plato will launch in 2026. And Plato is like Kepler and TESS, exoplanet finders on steroids. I mean, look at the cameras. I mean, seriously, they can't fit any more in. Importantly, it's going to be incredibly precise. It's going to survey wide swathes of the sky for weeks at a time. And so people will be able to hunt for these shark's fin occultations by exocomets orbiting their parent stars using Plato data. 2 years after Plato, if all goes to plan, ELT. This is a screenshot from last month, or actually maybe just a couple of weeks ago. It's getting there, it's taking time, but the 39-meter extremely large telescope will be there. Hopefully, it's planned in about 5 years. And on board will be Andes, the high-resolution spectrograph, with which people will be able to discover more Beta Pictoris-like systems. Because the light grasp of that means we'll be able to scour a much larger volume of the Milky Way with high-resolution spectroscopy to find them. And then finally, couldn't let it go, with 1 year after that, is the launch of Comet Interceptor. And the important thing is that Comet Interceptor is so named because the baseline plan of Comet Interceptor is to encounter a fresh, new, long-period comet coming out of the Oort cloud, or a new interstellar object discovered by Rubin. Fingers crossed. You may get a real close-up glimpse of an exocomet with Comet Interceptor. So, to summarize, Ecocomets, spell checker. Exocomet belts are common around young stars. We see them whenever, pretty much. It's difficult to avoid them with ALMA. Many A and B type stars, like Beta Pic, possess exocomet populations. We see these Beta Pic-like transits of exocomets across the disks of their parent stars. Small bodies, I didn't mention the numbers here, small bodies, including exocomets, are common around white dwarfs. The current estimate is somewhere between 25%, so a quarter and a half of all white dwarfs are polluted by the remnants of planetary systems falling onto their surfaces. There's a lot of planetary systems out there. And finally, the era of close-up inspection has started with interstellar objects with our ground-based telescopes. Let's keep our fingers crossed for Comet Interceptor. Thank you very much.
Thank you, Alan, for an absolutely incredible talk. Apart from the Ecocomets, but that's very, very 2020s. It is.
Thank you.
I'm in absolute awe of the precision of modern observational astronomy, that we can do this. I mean, when I was a kid, nobody would have thought that we could detect planets around other stars. And, you know, we're now detecting comets, which is just absolutely incredible. So we're coming to the end of the day. We've got to be out of here by 6, but I think there's enough time for 1 or 2 questions.